Recording in progress. All right. This is Saturday morning, 11:45 in the morning. It's still morning. So this recording that I'm preparing in my office, I have a pretty large board. When it was pandemic, I used to do online Zoom classes, which were recorded from here, pretty much pretending that you guys are sitting right across me, which is not the case. So this lecture is for Tuesday that I'm preparing. As I told you guys that Tuesday I will not be in the class, so no in-person class on Tuesday. I'll send two more reminders, one through Canvas and one through My Fresno State. And hopefully everybody will get the message and no one is going to show up on Tuesday at 9:30 in the Science Building, Science 2 building. So today we're going to talk about cycloalkanes. We have already discussed cycloalkanes. I have some models. I'm going to use the models. And my ambition is to finish the discussion of cycloalkanes during our 1-hour lecture today. So I'm going to set up the timer for 50 minutes and I might go for another 10 minutes. Okay, so this lecture is going to be for 1 hour, 50 minutes to an hour. And then, okay, timer started. And then you guys will be taking a 15-minute max quiz from 10:30 to 10:45, multiple choice questions. And as I said, a percentage of that, so let's say you get 20 out of 20. So a percentage of that will be like 2 out of 2 or 5 out of 5 or something. I don't know at this point. Will be added as bonus points to your second full test, whenever that happens. All right, well understood. I'm going to pretend that you guys said yes. Okay, so I'm going to pick up the pens. It's going to be a very similar style of lecture, except that it's going to be in my office. I'm really proud of my t-shirt. I would have done that if I were given the responsibility to take care of 4 children. No, no, I'm not that bad. All right, so we're going to talk about Chem8. I drew a couple of lines to kind of figure out that this is covered in my webcam. Yeah, I think that's perfect. Chem8, and the date for the lecture is 3/7/23. You know, pretty much the way I usually lecture in 309 in Science 2. And we're going to talk about cycloalkanes. Okay. Cycloalkanes. We already have initiated the discussion of cycloalkanes, and we figured out. Remember, I was using that metaphor, like if your grandfather wants you to buy the minimum number of poles to set up a fence around his, I don't know, his little cabin in the woods or in the rural area, and the answer is 3. So 3 is the minimum number of carbons that you need to have a cycloalkane. In order to make something cyclic, 1 is definitely not enough. It's just 1 pole. 2 is not enough because you cannot go around a place and make a cycle, right? In order to make a cycle, you need at least 3. Okay, you need at least 3 things, 3 poles. So the smallest cycloalkane is this. I'm just going to make sure that it can be seen. Yeah, it can be seen. So that's the smallest cycloalkane in skeletal diagram, in stick diagram. That's the next guy. This is the next one. And this is the biggest one. So we're going to only talk about these 4. Okay, names, 3 carbons, cyclopropane. This one, it can be read, it's pretty visible. I think it's recording in HD, so it should be all good. Cyclobutane. 4 carbons. If it were not cyclic, it would be a straight chain, and that would be called a butane. Alkane becomes cycloalkane. Just use your best logic. So butane becomes cyclobutane. Excuse me. Cyclopentane. Okay. And cyclohexane. All right. Let's do a little quick model and talk about few properties of the first 3 cycloalkanes: cyclopropane, cyclobutane, and cyclopentane. We are not going to spend a lot of time on those 3. We're going to spend a lot of time on the cyclohexane, okay? Because it's got a really interesting structure. Cyclohexane is found in many natural compounds. Cyclohexane is also found in, medicine and other chemicals that are used for some purpose that humans can be benefiting from. Okay, so let's look at their models. How do they look like? Okay, so I built like a long chain. I don't know how many carbons are there. 1, 2, 3, 4, 5, 6, 7, 8. This is octane, gasoline. Remember that this is a good way to kind of remember that this is gasoline, 8 carbons. Do not forget, it's important, this information from the preceding lectures or understanding concepts that we have gone through. It is important that when it's not cyclic, big things can turn around, right? This is octane, this is octane, this S is octane, right? This is octane, this is octane, this is also octane. This is also octane. This is also octane. This is also octane. So the structure doesn't change. All you're doing is you're bending, you're turning the molecule like as if this is a handle. In the older days, in very, very old cars, I think from the 40s and 50s, I don't know if the starter motor didn't exist. Maybe they did exist, but sometimes they would take like a metal handle, and from the front bumper, like the metallic bumper, like the chrome plated bumper, there would be a hole in the front. They would go in and crank using a manual force, and the car would start. So this just reminds me of that. It would be like a huge metallic cast iron handle. Okay, so single bond, carbon-carbon bond rotating. Okay. All right, so that's not really important at this point. Remember from the past that, excuse me, it's the allergy gift from the Central Valley. Okay. Before cyclopropane happens, think about propane, right? So propane has to become cyclopropane. So you need to connect carbon 1 and carbon 3. Okay, however you look at it. Carbon 1 and carbon 3 have to be connected. Now, every carbon is in sp3 hybridization. When it's in sp3 hybridization, the bond angles are 109.5 degrees, right? 109.5 degrees. Imagine 109 degrees. Pretty big number. This is a hydrogen, so this angle is also 109.5 degrees. The 2 hydrogens, roughly 109.5 degrees. Slightly different because it's not a perfect tetrahedron. Remember that. Now, I'm not going to. Hopefully I'll not break the model. Okay. I'll try to hold it here in front of so that you guys can see. When I'm trying to make cyclopropane, see, I'm really pushing things out of their comfort zone. Okay. When I'm trying to make cyclopropane, you can tell that I am really about to like break the bonds. So I am reducing the bond angle from 109.5 to some terrible number, really, really low number. So watch this. If it were a cheap molecular model set, it'll probably break. Okay, I got the triangle. It looks like those safety cones when your car breaks down or truck breaks down and they put it up on the side in orange color. What's the bond angle here? It's a triangle with identical sides, right? It's an equivalent like a symmetric triangle, whatever the name is in geometry. I forgot. ISO something. I can't remember. That bond angle of a triangle, the three bond angles of a triangle, they add up to 180 degrees. Since they're all equal, so it should be 180 divided by 3, 60 degrees. 60 degrees is pretty darn off of 109.5 degrees. So it should be 109.5 down here, okay? That should be the angle, and I'm forcing it to be 60 degrees. So what does that mean? That means you are really making yourself very uncomfortable by adopting a terrible conformation. But it has no choice. If it wants to be cyclopropane, it has to go through this joint pain. That was my wife calling me. I'm just going to text her that I'm recording. Yeah, just bear with me. This is part of the problem. Okay. So this is cyclopropane. So what can we say about cyclopropane? The bond angles of cyclopropane are 60 degrees. It's not a good thing. That means cyclopropane has, I jokingly call it joint pain, but it's not really joint pain, it's actually angle strain. That's the right word. Okay. So cyclopropane has joint pain in a funny way, but let's not use that word when we are talking about our organic chemistry discussion, having an organic chemistry discussion. It's called angle strain. Really bad angle strain. Angle strain means it wants to be 109.5, but unfortunately it's 60. 60 and 109.5, it's almost half. So this guy's under pretty bad stress. Okay. Something else about cyclopropane. I'll try to hold it the right way. This guy is planar. It's the fundamental rule of geometry. If you take 1 point, that's a point. If you take 2 points in space, that's a straight line. If you take 3 points in space, here, here, and here, that's a triangle. Here, here, and here, that's a triangle. That means when you have 3 points or 3 corners, and you're trying to make like a shape of that, that's always a plane. 3 things joined together, there is no way you cannot have a plane. It has to be a plane. 3 points means plane, right? So something else about cyclopropane, it's planar. I'm going to turn up this thing, making this chime and annoying me. Okay. Angle strain, and it's also the shape of cyclopropane is planar. That's all you need to know about cyclopropane. And remember, we talked a little bit about like substituted cyclopropane. You should be able to pull that one off. Let's practice maybe 1 or 2 very quickly. Okay. So when you have, when we have, what can we do it? Let's do it here. So when we have this molecule, you can call it Hershey's Kiss or jokes apart. If you have to name it in an IUPAC way, how would you name it? You know what this is. That's going to be the mothership. It's going to be the mother cycloalkane, cyclopropane. something cyclopropane, methyl cyclopropane. Methyl cyclopropane. If you have two of those, what should you call them? Dimethyl cyclopropane. Not that complicated. Well, there is a problem. Dimethyl cyclopropane. Where are the methyl groups? Does it really matter? It does matter, because you can have another cyclopropane with two methyl groups. How can you have that? Think about it. So this is what we have drawn. See, the structure is interesting. You don't realize that in 2D. If I just draw it here or hold it here this way, it looks pretty benign. It looks pretty boring. Okay. But once you look at it in 3D, you realize that the methyl groups are kind of like this is a plane, and the methyl groups are sticking out, right? So in principle, we're not going to talk about it. It's not part of the syllabus, but just for your curiosity, the methyl groups can be on the same side or on the opposite side. Okay. We will talk about that more when it comes to the hexagon, cyclohexane. What we are talking about, that this is not a complete name of 1,2. I already slipped it. It's already slipped out of my tongue. Slip of tongue. It's 1,2-dimethyl cyclohexane, because the two methyl groups can be on the same carbon. The two methyl groups can be on the same carbon. It can look like this. So we should specify where the methyl groups are. We have done it in the past. So this guy is going to be 1,2 dimethyl cyclohexane, and this guy is going to be 1,1-dimethyl cyclohexane. Make sense? Makes sense, because no one is there. You guys will hear me on Monday at 9:30. Okay. All right. So cyclopropane is done. I might have misspoken. I can't remember. I might have called cyclopropane cyclohexane. Just if I have done that, my apology. Just fix it. We were talking about not cyclohexane, but cyclopropane. I'm just getting paranoid that I might have done that. Okay. All right. So now the next question is, what did I do here? Almost broke it. Cyclobutane. Next contender. I need one more, the connecting thing. Let's make cyclobutane. 4 corners. Okay. You can tell that building a cyclobutane from a straight chain molecule is not as terrible as building a cyclopropane. It's bad, but it's not that terrible. Cyclobutane. You might think it's planar, but it's not a perfect plane. What happens is 3 of those carbons, excuse me, I might sneeze pretty soon. I think it's on the horizon. The clouds are there. The sneeze clouds are, I can almost see them. Carbon 1, carbon 2, carbon 3 will be on plane. And oftentimes the 4th carbon kind of sticks out, kind of like a little, like slightly folded. And that fold could be here. The fold could be somewhere else. Okay, it's not a perfect plane. almost planar, but not a full plane. So just keep that in mind. Does cyclobutane have angle plane? It does. What does the angle look like? It's approximately 90 degrees. Because of that little bend, little turn, little fold here, slight fold, okay? It's also conformation. Remember, this is conformation, how the molecule kind of bends. Okay, we're not turning, but it's kind of like flipping. The molecule is kind of bending, right? Okay, these are conformations. We'll talk about that in few minutes. Cyclobutane has angle strain. The angle is approximately 90 degrees. It's still pretty low from 109.5 degrees, right? So the bond angle of cyclobutane is approximately 90 degrees. This sign is important. You cannot call it 90 degrees because it's not 90 degrees. It's about 90 degrees. Okay. It also has, this guy also has angle strain. Okay. And it's kind of planar. I'm going to use that sign. Kind of planar, not fully planar. Okay, we are recording. Everything seems to be going okay. Yeah, I'm just making sure that I'm zooming and recording after a long break. So I'm just making sure that everything is fine. Okay, all right, sounds good. So that's cyclobutane. I'm not going to waste time like doing nomenclature of substituted cyclobutane, right? Ethyl, methyl, you guys figure it out. You already have the ammunitions. You know how to do it. So you guys figure it out. Not that bad. Okay, let's make the next one. All right, so cyclopentane. Pentagon, famous pentagon. Pentagon, when we are making pentagon, you can tell that there is hardly any resistance. I don't really have to like force it to go into a cyclopentane or pentagonal shape. It's pretty easy. You know, they kind of line up. So the bond angles, I don't want to talk about the bond angles. It's pretty darn close to 109.5 degrees, but it's not exactly 109.5 degrees. It's pretty close. It's little less than 109.5 degrees. What about cyclopentane? Does it have angle strain? Very little, almost negligible angle strain. Almost no angle strain. Okay, the bond angle very close to 109.5 degrees. It's less than 109.5 degrees. Okay, so it's a pretty happy cyclopentane cycloalkane ring. It's not bad at all. Now, what about the shape? The shape is pretty interesting. I always joke about it in the class that because you guys don't write, you know, in the older days when I was a brand new immigrant here in this country as a foreign graduate student in University of Nevada, Reno, the way I used to communicate with my family back in India was by writing letters and throwing them in an envelope. So if you look at the shape of this object, and if you look at it from the side, and then if you look at it from the edge, you will always find that 4 of the carbons make a plane. I'm trying to hold it the right way. Make a plane, and 1 carbon, I think that's on your right side. That's on your right side, that guy here, this dude. that's sticking out, kind of like an envelope, as if you know, this is where you're going to stick the letter, and this is the part that you're going to fold, and you're going to put glue here and seal the envelope. It kind of looks like that. So obviously it's kind of obvious and you know, intuitive that the shape of a cyclopentane is often called the envelope shape. Okay, it's not planar. I'm going to draw like a long line here. The shape of it is called envelope. Envelope shape. Okay. Remember that it's not always that one specific carbon that's going to be up. It can be this height, this carbon. It can be the other carbon, and it can go up or it can go down, either way. Okay, so the bottom line is this whole molecule is probably going to be doing its cyclic dance all the time. It's going to kind of like turn around. Imagine cyclopentane is floating around in space in your classroom or in my office at this point. It's probably doing this constantly. Okay, and at every, you know, if you can take a snapshot using a camera still picture, it'll look like 4 carbons are planar and 1 guy is sticking up or sticking down where you fold the envelope. Make sense? Let's stare at the board maybe for 10 seconds, not more than that. Cyclopropane, you should know the names for the next exam and for the quiz that's going to be happening right after this lecture. Cyclopropane, cyclobutane, cyclopentane, cyclohexane. Okay, you should know the names. They're not that difficult. Count the number of carbons and then go from there. What about this guy? Well, something else, like if you have substituents, it'll be methyl cyclohexane, my bad. Methyl cyclopropane. 1,2-dimethyl cyclopropane. It could be 1,1-dimethyl cyclopropane. It could be 1,2,3-trimethyl cyclopropane. Why not? Right? It could be 1,1,2,2,3,3 hexamethyl cyclopropane. Imagine cyclopropane with every corner occupied by a methyl group. 2 methyls here, 2 methyls here, and 2 methyls here. That's good. That's going to be like a pretty interesting looking molecule. Okay. Every corner has 2 methyl groups. That'll be 1,1,2,2,3,3 hexamethyl cyclopropane. You could have a methyl group here and an ethyl group here. How would you name it? On the butane, cyclobutane ring. Well, ethyl comes first, methyl comes second. You should start numbering from here. 1, 2, 3. 1 ethyl, 4 methyl cyclobutane, something like that. So I'm assuming that you can pull it off. Cyclopentane, same thing. Cyclohexane, same thing. We haven't talked about cyclohexane yet because that's going to take up quite a bit of time. Planar, kind of planar, pretty planar, but not really planar. 3 of them are always planar. 1 is slightly up or slightly down. Okay, remember that. 60 degrees bond angle. It's not approximately 60 degrees. It is 60.000 degrees because it's a triangle, man. There is nothing, no other degree can happen here. The bond angle is 1/3 of 180. That's it. Geometry, physics, or whatever it is, mathematics. Roughly 90 degrees, planar. This guy has maximum problem being this way, being triangular. It wants to open up. That's why cyclopropane rings are most reactive. Remember that, because they don't like to be cyclopropane ring. They want to be open and get rid of their strain. I mean, I don't want to be in a weird conformation if I don't want to. I mean, unless I'm doing some yoga or some strange postures to, I don't know, build my muscles. If I am going through a midlife or end life crisis and start doing some crazy, stretches and stuff, then I'm going to be under strain. And I will want to get rid of the strain by becoming normal conformation, which is this, comfortable, right? So they are most reactive. Remember that, it's planar. Almost planar has angle strain, not as bad as this guy. This guy has envelope shape and it's pretty happy. It has very little angle strain. Okay, that's what we have discussed so far. All right, ready for cyclohexane? I'm ready. Let's do it. I need one more. I need one more carbon. I'll do it behind me. I can't show it to you first. Yeah, no, right. If I just hold it from the front, okay, it looks like a cyclohexane, like a perfectly planar cyclohexane, like a hexagon, right? I wish you guys were sitting there and I could have had like a dialogue and conversation with you. Okay. This is what it looks like. This is not what it looks like from the side. Ready? What does it look like? It looks weird. It looks like if it had something sticking out from here, it would look like one of the things that you have in your home or office or wherever, where you can sit, you can lean your back here, and you can put your feet down here. This is your footrest. This is where you sit, and that's where you put your back. I'm just having problem. Kind of like this angle. It's called a chair conformation. Okay, it's like a chair. This is where you sit. These 4 carbons, 1, 2, 3, 4. This is where you put your back, and this is where you put your foot down. How do you draw this cyclohexane chair from the side? And the interesting thing is, when you're building a cyclohexane chair, there is no forcing. It's like the ideal student wants to do its homework. There is no stress, no tension, no agony, no drama in the morning of Saturday when the mother is asking the kid to go and study. Like everything is like ready. His notebooks are ready, his textbook is ready, he or she has had his or her breakfast, no fuss there. Everything is perfect, goes and sits down, and homework starts happening, and the cyclohexane ring forms. Every carbon around cyclohexane ring has a perfect tetrahedral shape. This is perfect tetrahedral. Okay, if you just focus here, 109.5 degrees and 2 hydrogens sticking up and down, this is a tetrahedral. If you think about that cube that we talked about, these 2 carbons are at the bottom of the cube, these 2 hydrogens are on the top of the cube. It's not a perfect tetrahedron, but it's as close to a perfect tetrahedron as you can think about. Actually, the angles are almost 109.5 degrees because of the shape of the molecule. This cyclohexane chair conformation makes all the bonds 109.5 degrees. Okay, so I'm going to draw the cyclohexane chair first, my quick way, and then I'm going to teach you how to draw it taking your time, and I'm going to teach you like a little trick. The way you do it fast, it'll take you some time. You don't really have to learn exactly how to draw a cyclohexane chair, but it's kind of fun. A lot of actually molecules. I can't think about any on top of my head. Tylenol, aspirin, ibuprofen, they don't have cyclohexane ring. Something has cyclohexane ring. I'll figure out, and I'll let you know on Thursday. Okay, this is how you draw. This is the 2D representation. 2D representation is boring. Hexagon, right? The 3D rendering of it will be this way. It's a chair, okay, and it's called, this is the 3D rendering, and this is called a chair. Okay, and it's called a chair conformation. This is a conformation. We talked about it. Conformation happens from turning a bond. Remember, we did that for ethane. Remember how you got the hydrogens on the second carbon right behind the front hydrogens, carbon hydrogen bonds, and that's called eclipse. That's a bad conformation, high energy, and then you turn it by 60 degrees, then you get the perfectly, perfect conformation where everything is farthest away from each other, and that's called staggered. We did that yesterday. Not yesterday, day before yesterday, Thursday. Okay, we did that on Thursday, right? We if you look into your notes and if you look at the pictures, that's how we have done it. So this is a chair conformation. Okay, what I'm going to do now is I'm going to show you that the in the rest of the conversation lecture, I'm going to focus more on cyclohexane chair. What I would like to show you first right now is that, okay, just in a qualitative way, say, I'll hold it away from you. The perception is difficult to kind of pull off sometimes. Sometimes I'm still like learning. Okay. So on your right is the footrest. I'm moving my finger. This is where the footrest is. And this is the backrest, right? This is the backrest, right? This is where you sit on the chair. Now realize that something funny can happen. Okay? Something funny can happen. This molecule can flip. So I push the footrest up. Now it does not look like a chair. It looks like something that floats on water and takes people from one place to another. It looks like a boat. Okay? This is not a good conformation. This is actually a bad conformation. I will explain the reasons in a minute. Now, I push the bottom up. What if I push the backrest down? What if now I flip this side down? If I do that, I get the other chair. On your right-hand side, this side, you had the footrest. And on your left-hand side, you had the backrest. But now it's opposite. On your left, you have the footrest. On your right, you have the backrest. That just happened. Let's do that, okay? So this is the backrest. And this is the footrest. Okay. Let's hold the footrest up, what we just did. So we are flipping the molecule one at a time. When we flip the molecule, I'm going to draw it slightly differently. You get something that looks like that. Okay, let's go back to that original molecule. Okay, chair, left side is the footrest. Now it looks like a boat. Now it looks like a boat. Both sides up. I will tell you why this is a bad confirmation. So chair to boat. That's also a confirmation. Chair is a confirmation, boat is also a confirmation. Then you flip more by pushing this side down. Then you get the other chair with the sides kind of flipped around. This is another happy chair. What's here for you guys to learn? Well, the cyclohexane ring has a chair conformation. That's where it likes to stay at. If you flip the molecule both at the same time very quickly, if you do it quickly, then chair to chair, chair to chair, right? This will be a good time to invest in a molecular model set. You can go and search under Amazon or eBay, and they're pretty cheap. I think I've seen the cheapest on eBay was like $11.99 or something, including shipping and handling. Amazon might be a little more expensive. I have seen one of my 128A students last semester buying the cheapest model set, and he regretted because the bonds were so flimsy that it doesn't hold the shape very well. It was very frustrating. He ended up buying a better model set, and I kind of felt bad that I suggested to them to buy a very cheap model set. But maybe you should go to Amazon and spend maybe $4 extra to buy a decent model set that has decent reviews. Just buy it from Amazon. This will be a really good time to invest in a model set. This is high time. Okay, so both sides, if I turn, push, and pull, then it becomes a chair. And remember that this is a chair. If I move my hands to here and here, this is also a chair. The right side is down, left side is up. If I move my hand to the next carbon and next carbon here, this is also a chair. Right side up, left side down. Right side down, left side up. So it's kind of like a crown. Up, down, up, down, up, down, up, down. Okay? Like up, down, up, down, up, down, up, down, up, down. It's very symmetric. This whole thing is very symmetric, but it's pretty interesting, isn't it? So if you flip only one side, terrible. Why is it terrible? I'll explain it to you in a second. Okay, so the bottom line, what you learned about cyclohexane, it has a chair conformation, one side up and one side down, and that's true for every diagonal corners. Down and up, up and down and up and down. So just because the shape of the molecule. And if you flip it upside down, it's the same thing. What used to be down, up, when I flip it, turn the molecule 180 degrees, the upside becomes out. Okay, it's now facing toward you. This is facing away from you. Facing toward you, facing away from you. Facing away from you, facing toward you. Make sense? It'll probably be best if you have a model. And then we talked about the fact that if you do a half flip, only one side, it goes to a terrible conformation. Both. Why terrible? I'll explain. And then if you bring the other side down, then it's all happy again. And cyclohexane, if it were floating around in air in my office, it's probably constantly doing this. It's constantly doing that, not necessarily this way. Okay, the whole molecule is probably doing this because it's got some flexibility. Okay, I'm going to erase the board. So take a look at the screen. and make sure that it makes sense. I'll take a look at the clock, the timer. Where am I? Okay, let's expand our discussion a little bit more. I have 6.5 minutes left to become 50 minutes. So that means after 6.5 minutes, I have 10 more minutes. So 15 more minutes left for the lecture. That's not terrible. Given my track record, it could have been worse. I'm not proud of it. I'm feeling bad about slowing down all the time. Okay, let's erase everything. That's what the holy man told the supreme power. Erase all my memory. Make me forget everything. That's not what he said. Someday, I'll be punished for saying all the horrible things. I think my punishment has been going on through my life. All right, people, let's make the molecule a little bit colorful. So, how do you draw a cyclohexane? Well. Draw two horizontal lines. It can be imaginary when you get good at it. It can be like light, slightly like faint lines. They're kind of like a railway track. Okay, let's do that. I'll do it in green because green is hard to see anyway. All right, you can barely see it. Yeah, we can barely see it. Okay, all right. That's the first step, two horizontal lines. The next step, draw a slanted line. That's going to be one of the 5 CC bonds in cyclohexane. You drew a slanted line, I don't know, like 45 degrees, 30 degrees from the vertical line. You go about twice that length. If this is about that much, you go a little bit more. Okay, draw another line. I screwed up. It should be parallel. It should be a little more slanted. Yeah, it'll do. So 2 parallel lines slightly slanted. Got it? Then starting from here, make a triangle here, like a triangle, not perpendicular, not horizontal, not vertical, but in the middle. Draw a line, go about 2/3 the whole distance. If that's the whole distance, entire distance, go about 60% of that length, roughly. Okay. Then from here, draw another line that's same length and same angle. You're done. Join the dots. That's it. Woohoo! Cyclohexane chair. That's cyclohexane chair. Yeah, this is how it looks like. Cyclohexane chair. Now, what I'm going to do is I'm going to put the hydrogens of around cyclohexane in 2 different colors. Okay. Let's do that with the model first. Okay. I'll do it right in front of you. I'm not doing any funny business here. So blue, And blue, there is one that's broken, this guy. That's the first casualty with my model set. Blue, blue, and imagine these are hydrogens and blue. Okay, they're kind of like three antennas sticking up and like three landing gears. Okay, think about it like this. Okay. Let's draw them. So this is the high point, high, low, high, low, high, low. Take the high points and go up a hydrogen, go up a hydrogen, go down a hydrogen, low point, go down a hydrogen, go down a hydrogen. Okay. The rest of the hydrogens are going to be in red color. Red, red, red. My timer is going to beep pretty soon. What? What happened to my timer? Timer already beeped. Okay. I think I started around 12:45. So according to the okay, 10 more minutes. 10 more minutes or 12 more minutes. So all the red hydrogens are in. If you look carefully, let me just do this. If you look carefully, there is a trick to drawing these hydrogens. I will teach you. Now I'm going to go pretty much with my wall clock that says it's 12:35. It's going to be another 10 minutes or so. That'll be like roughly an hour-long lecture. Okay. So the red hydrogens and the blue hydrogens, they look different, isn't it, on this cyclohexane weird chair conformation. These guys are perfectly vertical, right? Pointing up. These guys are perfectly vertical, pointing down. But these guys, look, they're kind of funny. It's kind of like sticking out. If you look at the molecule from top down, if you look at it from top down, the blues kind of cannot be seen. Blues are basically, the blue hydrogens are basically disappearing with the cyclohexane ring. But the red ones are sticking out. Right? Out of the periphery, out of the circular ring, they're sticking out away from the center, right? So there are two different names for them. The blue ones, up and down, they're called axial hydrogens. That location is called axial. This is kind of like along the equator of planet Earth, the sticking out from the equator. They're called equatorial hydrogens. I'm going to write it down. So the blue ones are called axial, AXIAL, axial hydrogens. The red ones are called equatorial. You must be wondering, why is Shantanu laughing? Is he having some misfire in his brain between the neurons, which is happening all the time since my birth? I think all the stars were kind of lined up like wrong when I was born, unfortunately. I'm sure my parents wondered about that. What's wrong with our youngest son? The eldest daughter and the next son were like perfectly fine. This guy is kind of broken, born broken, not like born. What is that? Breaking bond. another spin-off story from there, like Mandalorian, will be like born broken. So, not born broken, born broken. Let's flip it. Ready? I'm going to do it very fast. Uh-oh. This is a magic trick. Blue became red and red became blue. Let's do it slowly. All right. When you're flipping it, equatorial becomes axial and axial becomes equatorial. That's what happens. I can't help it. I'm sorry. You know what? Let me just use my chair. Not our department chair, but this chair. What am I doing here? I'm doing something wrong. Okay, there you go. Okay, can you guys see? You can't really see it. Something is wrong. There you go. Can you guys see it? Yeah, you guys can see it. I'm going to push it behind a little bit. Okay. All right. Let me, without knocking this thing out, let me just try to like draw this molecule after flipping. So let's number the molecule. Number the cyclohexane ring. We have like 5 more minutes left. Okay. Let's start from here. 1, 2, 3, 4, 5, 6. Okay. That's the low point. That's 1. 1 kind of going out toward you, 2, 3. Again on the whiteboard, 4. Behind the whiteboard, 5. And behind the whiteboard, 6. So this is on the whiteboard. This is on the whiteboard. These number 2 and number 3 are out. Number 2 and number 3 are out. Number 5 and number 6 are behind the whiteboard. We don't use dashed lines and wedges here because that's going to drive everyone completely crazy out of their mind. Let's not do that. We have to kind of get used to this rendering or this representation. How do we draw the cyclohexane chair this way? Okay. So when we are flipping it, we are pushing 1 up. In order to flip, we are pulling this guy up and pushing 4 down in order to flip. Okay? After flip, the ring flips. What used to be down goes up. What used to be up goes down, right? So I'm going to try to like draw a decent cyclohexane ring again. Okay, that's number 1. That's now up. 1. This came down. 2 came down. 2, 3, 4, 5, and 6. And the colors of the hydrogens have interchanged their axial equatorial locations. Now, the blue ones are equatorial. Uh-oh. There's a ghost in my office. The blue ones are equatorial and the red ones are axial. Down, easy. Down and down. That they're easier to draw. Up, up, and up. They're easier to draw. That's how when a cyclohexane chair flips, what used to be equatorial becomes axial. What used to be axial becomes equatorial. 3 more minutes. What I would like to teach you is how do you draw the equatorial bonds. Remember, let's do it here. I'm going to just show it to you, like how do you draw the equatorial bonds? Equatorial bonds are drawn this way. When you're drawing the equatorial bonds, I'm going to pick a different color. Okay, so let's say this is 1, 2, 3, 4, 5, and 6. And you're trying to draw an equatorial bond from number 1. You can't screw up the drawing because I'm probably going to ask you some detailed analysis and analytical questions regarding the shape of the molecule. I'll present you like 2 or 3 different shapes, conformations. I'll ask you to pick the right one or the wrong one. Okay. So if you draw the equatorial this way, terrible. No mercy, no pity. That's terrible. That's not how the bond is. That's not how it looks like here. Okay. The equatorial bond, this is the equatorial bond. That's not inside the ring. That's kind of outside the ring. That's sticking out, right? So it has to be here somewhere. If you draw it this way, is it right? Not really. Is this right? Wrong. What's the way to draw it? Well, when you draw it, if you're starting from carbon 1, then you ignore the next door bonds. Carbon 1, carbon 6 bond, you ignore. Carbon 1, carbon 2 bond, you ignore. What's the next carbon-carbon bond? 6, 5, and 2, 3. Pay attention. The equatorial bond must be parallel to the next door CC bond. So this bond, equatorial bond, has to be parallel to 2, 3, and 6, 5. Equatorial bond has to be parallel to the next door CC bonds. So what's the do? Oh, almost broke it. No damage done. So from 6, the CCH bond, the equatorial bond, must be parallel to not 6,1 or 6,5, but the next 2 carbons, 1, 2 or 5, 4. So it should be parallel to that. Parallel to this bond. Okay, that's how the equatorial bonds are drawn. I'm just going to finish this lecture by saying one thing. Okay, so axial becomes equatorial, equatorial becomes axial. And I told you that the chair is good, boat is bad. The reason chair is good, boat is bad is because of the following reason. I'm just going to talk about that briefly and then go from there. You already learned that staggered is good, eclipse is bad. Okay. Low energy, chair, low energy, chair. Good conformations. This is high energy because this is a boat. This is a boat. This is a chair. This is another chair, right? Chair is good, boat is bad. Why? Let's use the module. For this reason. When it's a chair, this is a chair. Look down any 2 adjacent carbons. Look down this bond. Okay. Yeah. Look down this bond. What does it look like? The 2 carbons and all the hydrogens. 2 carbons and all the hydrogens. Why am I having? This is why I could not have become a fighter jet pilot. Okay, I think you guys got it. If you look down this carbon and this carbon, that was the problem. This carbon and this carbon, okay, they're you're looking at the Newman projection. You're looking at the Newman projection, and you can tell pretty easily that the two carbons, all the hydrogens and all the bonds are staggered. They're not eclipsed. If you look down any other CC bond, let's take this CC bond. This CC bond on your right, close to my head. Okay, this one or this one. They're both staggered. So every adjacent carbon is staggered with its next door neighbor. That's the case in cyclohexane chair. What about boat? Let's make a boat. We made a boat. This is a boat. Not a goat, not a bloat, but a boat. Kindergarten. I know exactly how to write the rhymes to teach the kindergarten kids cyclohexane chair. Okay. These two staggered. No problem. Good, right? What about the side of the boat? If the boat is going to float, getting ideas. If the boat is going to float like this, and if you're looking at its direction, the part where the boat kind of folds up, right? Look at the sides. They're not staggered. They're eclipsed. These two are eclipsed, and these two are also eclipsed. So two sides of the boat are in eclipse conformation. That's terrible. That's not good. So these two carbons and these two carbons are eclipse. Eclipse conformation. That's terrible. I don't know how my spelling conformation. You figure it out. So this is bad. Eclipse means bad, terrible. On top of that problem, there is an additional problem for boat. Look at the top of the boat, where in Titanic, those kids hung out most of the time before the ship went down. They kind of looked outward, and this is like the other way you can stand on the boat. This red hydrogen that was at one point, axial or equatorial, and the other guy which was axial or equatorial, they are almost like kissing each other like that. The location of those Venus and Jupiter the other night, 2 nights ago, they were so close it looked like they were going to collide. But that's illusion, right? They were calling it, they have a name like star kiss or kissing star or something like that. They're too close, they're bumping into each other. This is a problem. This is not fun for human beings, depending upon how they feel about each other. It could be fun or not fun, unfun. This is not good for the hydrogen atoms. This is called flagpole interaction. When you have the hydrogens, one hydrogen from here and one hydrogen from the other end, extremely close, this is called flagpole interaction. And this is also bad. So if I ever ask you, why is boat worse than chair? There are two reasons. Eclipse conformations along the two edges, 4 carbons are in eclipse conformation to each pair here and pair here. And to make things worse, you have a flagpole interaction. That's why boat is bad and chair is good. In chair, every 2 adjacent carbon is in staggered, are in staggered conformation. I'm going to stop right now. I think I went over a little bit, maybe 5 minutes or so. I'm going to make the quiz shorter, 10-minute quiz, just a few questions about what we discussed. I'm going to see you guys on Thursday in-person class. I'm going to send you a couple of reminders just to make sure that nobody it shows up on Tuesday morning. You guys don't see it, so no point wishing you happy weekend or something. Have a good Tuesday, and I'll see you guys on Thursday. I can return the quiz. I already returned your quiz exam, so it's not a big deal. I'll have to mention that in the 128B lecture. All right, I'm going to stop and see you soon. Bye. Oh, stop the recording right now.